Well, hello again, everyone. Welcome to our discussion of section 11.3, which will be about another conic section known as the hyperbola. So, before we jump into the details of what a hyperbola is and what graph, equation, and what are the other details of it, I wanted us to look back at the equation for an ellipse and make a quick comparison between the equation of an ellipse and the equation of a hyperbola before moving forward. I think this causes a lot of confusion if we don't clarify it right from the start, and so it's a good idea to just make a visual comparison. This will be a visual comparison between the formulas for an ellipse and the hyperbola. And that way, when we delve deeper into the hyperbola topic, things will be much more clear. At least that's what I think, or that's what I'm hoping for. So looking back at section 11.2, when we covered the equation of an ellipse, we had the equation of an ellipse was looked as follows. It was x squared over a squared plus y squared over b squared equals 1, right? And notice that a was represented always, or this quantity a squared was associated with the major axis, and b squared was a quantity associated with the minor axis, right? Now we could then switch these denominators. We could do x squared over the b squared, which is associated with the minor axis plus y squared divided by the quantity associated with the major axis equals to 1. So here, in this situation, you could change the setting for the denominators. You can interchange them. So you could put the a squared under a x squared, which would make it a horizontal ellipse, right? This would be a horizontal ellipse. With its major axis directed along the horizontal axis. And this would be with the minor axis. This one would have the a squared associated with y squared, so it would make it a vertical ellipse. It would say something about the orientation of the major axis in the ellipse. But notice that this quantity a squared and b squared could change between these two fractions, and this was this ratio plus this ratio, right? With hyperbola, so this is the equation of a hyperbola with its center at the origin. Notice all the conic sections we've been talking about so far, the circle, the ellipse, the parabola, and now the hyperbola, they all, so far, we've looked at their formulas such that these conic sections were centered at the origin, and this is no exception so far. But in section 11.4, we will look at situations where these conic sections are centered off origin at some other point within the Cartesian coordinate system. But for now, this is also represents the equation of a hyperbola with center at the origin, which is 0, 0, right? And this is that equation. We have x squared over a squared minus y squared over b squared equals 1, either that or y squared over a squared minus x squared over b squared equals 1. So notice the difference between, the main differences at least, between equations for ellipse and equations for hyperbola. So for the main thing, one of the most eye-catching things you'll see is that ellipse is two ratios added together equal to 1. With hyperbola, it's the difference between two ratios that equals to 1, right? The other thing that you should notice right away is that notice in the ellipse, the x squared term it stays stationary. It's the first term with the major axis switching its spot either underneath x squared or moving to becoming a denominator for the y squared term. And of course that will affect whether this is a horizontal ellipse or a vertical ellipse. So where the quantity associated with the major axis is, whether it's under the x squared or y squared, determines whether it's a horizontal ellipse or whether it's a vertical ellipse. So we learned that last section. But in hyperbola, now the major or a squared term, I should say, a squared is associated with the vertex. So I will repeat these again and again. So a squared or a squared equals the quantity associated. So I should say that a squared is quantity associated with the vertices in hyperbola, with the vertices. Okay, so B quantity, which now in the formula is squared, is not associated with any of the vertices. Remember with ellipse, both A and B were associated with the vertices of that ellipse. The A quantity was associated with the end points of the vertices along the major axis, and B quantity was associated with the vertices that are along the minor axis, so the shorter axis and the longer axis. But here in hyperbola, the B is not associated with, it's an important quantity, but it's not associated with the vertices of the hyperbola. In hyperbola equation, only quantity A is associated with the two vertices of the hyperbola. In other words, in ellipse we have 4 vertices. 2 of them are along the major axis, 2 of them are along the shorter axis, which is called the minor axis. In the hyperbola, we only have 2 vertices, not 4. So we have the A quantity is associated with the location of the vertices, those 2 vertices in a hyperbola. So that's one thing you should notice. And it's the difference between 2 ratios. And also that notice that here in ellipse, the x squared, y squared do not swap spaces or spots, right? X squared is always the first, is the numerator in the first ratio. Y squared is the numerator in the second ratio. And only the major minor axes quantities swap spots in the denominator, right? But in hyperbola, it's the opposite. The vertices of the hyperbola always form the denominator or the quantity associated with the location of the vertices always forms the denominator of the first term in a hyperbola. And the B quantity is associated with the denominator of the second fraction. But in the hyperbola, it's the numerators that swap, right? In the ellipse equation, the numerators were fixed. It was the denominators that swapped spots. But in hyperbola, it's the denominators that are fixed. A squared, B squared, B squared. But it's the numerators that swap spots between one form or the other one. So what's the difference? Well, if you have the vertices the quantity associated with the vertices of a hyperbola forming the denominator of the x squared term, then you have a horizontal hyperbola. So let me write that here. So this is a horizontal hyperbola. And if the quantity associated with the vertices of the hyperbola forms the denominator of the y squared term, then this hyperbola opens upward, and we have upward and downward, and we have a vertical hyperbola. Okay, and the horizontal hyperbola means that the two pieces of the hyperbola open left and right horizontal, in the horizontal direction. Okay, so this is very important, the differences between the equations, because they're so similar but they're so different at the same time. So I encourage you to watch again this segment of the video that I talk about these differences as many times as necessary, so you feel comfortable with, okay, that's what's going on with the equations of the ellipse, and this is what's going on with the equations of the hyperbola. So this is just to start with, so we don't confuse the hyperbola equations with the equations for the ellipse. Okay, so now that we've talked about that, I think we should talk about the anatomy of a hyperbola graph. So one thing, we've been talking about conic sections, and I've explained that we call them conic sections because they can be drawn or obtained by obtaining a cross section of an upside down cone. So let me draw a similar picture here for the hyperbola. So if we take this upside down cone, something like this, like that, and with the dashed line forming the other side. So the hyperbola would look something like this. Like that. And then it's got two pieces, and that's one piece. The other piece would be the cross section here. And then coming back like that. Okay? So these two pieces together form the hyperbola figure, or the conic section for the hyperbola. So this would be that one and that one, these two together. Okay, so what is the anatomy of a hyperbola? And so let's draw that, or the basic anatomy of it at least. So here we have the horizontal axis, and of course the vertical axis, like that. And so we usually have, or not usually, always have, a set of asymptotes that are going through the origin for the hyperbola that goes, that has its center at the origin. Like that. And then another one going like this. And then each of these components, of course, we will talk about in deep detail in the coming minutes. And so here's another asymptote. Okay. So the hyperbola, this is just an example of a horizontal hyperbola. So I'm going to draw it like this, and like that. I wish I could make my drawings more symmetric, but this is the best I could do. And then, so this would be the vertex, these 2 points. So that's a vertex. That's also a vertex. So only 2 vertices. These 2 dashed lines, these are the asymptotes. Asymptotes or asymptote, and then this is another one like that. This is, of course, the center. So this is the center. These are the vertices. That's the center of the hyperbola. And this is why I say I wish I could make my drawings more symmetric, because this distance from here to here and from here to here should be equal. And I apologize if it doesn't look equal, but they should be equal. Okay, and so what else we should talk? We talked about the center, the vertex, the 2 vertices, the asymptotes. Oh, the focus. So the focus would be somewhere here. And so this would be one of the 2 focal points or foci of the hyperbola. So that would be one focus, and this would be another focus. Okay. So we talked about the vertices, asymptotes, focus, and the center. Okay, so what is a hyperbola? Hyperbola is the set of all points, that means the red lines that you see, the set of all points such that the difference in the distance between any of those points and 2 fixed points is always a constant. So that means if I take, suppose if I take, let's say, a point like that. Okay? If I take that point, let's call it point x comma y, then the distance between that point, the distance between that point and any of the, so this one, this focus, and that focus, that focus right there. So the vertex is here, and that's the focus, and this is another focus. Let's connect that. Okay. So the hyperbola represents all such points. All such points forms these 2 curves you see in red, such that the difference in the distance between that point and that focus and that distance is always a constant, and it's equal to twice a. And we will talk about that. So, but let me write that down. This is just the basic anatomy. At this point, I want you to just note the basic anatomy of a hyperbola, and also I want to give you a description of this, what this figure is trying to say. So a hyperbola is the set of such that the difference in the distance between each point on the curve, that could be on this curve or on that curve, it makes no difference, and I picked one example being that point. Each point on the curve, between each point on the curve and the two focal points is a constant. Is a constant equal to 2a with a being the distance from each vertex to the center. So in this figure that I've drawn, A would be, so this would be positive A, and this distance would be negative A. So we're saying that if you take this length, subtract this length, that would be equal to 2a, twice this distance, for any point along these curves. So if you pick a point such that that difference is not true, is not equal to 2a, then that point does not belong on that hyperbola. Okay, so these two curves define all such points such that if you take their distance, the distance between that point and this focus, and subtract from it the distance from that point to this focus, it's always equal to a constant, and that constant is equal to twice the length of the distance between the vertex and the center of the hyperbola. Okay, so all of this is talking about the geometry of the hyperbola. And your book gives so I've said this in words, what defines the points on a hyperbola. Your book gives the same thing in symbolic form. So let me do that here. Just it's not that important, but it's important because it's a symbolic way of saying the same thing. This is saying that what hyperbola is in words, in plain English, but symbolically this would be distance between, absolute value of the distance between the point and one of the focal points, and the distance between the point and the second focal point. That difference is always equal to 2a. Okay, so what I've boxed here is saying exactly what you see, what you read here, but in symbolic form. Okay, and the geometric interpretation of all of this is what you see in front of you. Of course, it would be more symmetric if my drawing was correct. So this is a graphical way of saying what hyperbola is. This is just using plain English to explain what hyperbola is. And this is basically making the same statement in symbolic form. So basically all three things, this, and that, say the same thing, more or less. Okay, so now let's narrow this down to more fine-tuned details about the hyperbola. So let's title this as the hyperbola with center at the origin, 0, 0. Okay, so I want to start with the equations first, and I'm going to put, I will do one graph for the horizontal hyperbola and one graph here for the vertical hyperbola. and I will start with the equations. So x squared over a squared minus y squared over b squared equals 1. Notice here a, which represents the vertices, the location of the vertices of the hyperbola, is under the x squared term. So our hyperbola, based on this equation, is horizontal, opening left and right. By the same token, on this side, we have y squared over a squared minus x squared over b squared equals 1. So here, the location of the vertices of the hyperbola is the denominator of the y squared term. So in this case, the hyperbola opens up and down. So it is a vertical hyperbola. So let me write that down here. This is the equation for the horizontal hyperbola. This is the equation for the vertical hyperbola. Of course, this is centered, we already said it, but centered at 0, 0, centered at 0, 0. Okay. All right, so let's draw the pictures for these. Like that. And of course the vertical axis. Like that. And so let me draw what we call the central box. I will talk about what central box is. So the central box would be, well, I will draw the asymptotes first. And so the asymptotes going like that, and then another one like this, and I will do another set of asymptotes on this side. Like that, and another set of asymptotes like this, like that. Okay, so the central box would be something like this. It would be something like that. And then again, my drawings are not symmetric, and so if I drew this, let me correct this asymptote with a thicker marker. So I'm going to just make a correction so that this is going better, going from like that. That's better. And then that set of asymptotes should go through like that. So these should be equal distance. These points should be equal distance from the horizontal axis. From here to here and here to here should be equal. From here to here and here to here should be equal. That's why I say that I should do a better job of drawing these symmetrically. But my point of drawing this like this is to show you where A and B are with respect to this central, what we call central box. So here this would be the hyperbola going like this, and on this side it will be like this, like that, okay, roughly. So roughly it would be this area. And the vertices, so this would be A comma 0. This vertex would be minus A comma 0. So what are these 2 points? These points are the B values. So 0 comma B, and that one is 0 comma minus B. Okay, minus B. And please ignore this lighter blue line. So the thicker one is in a better it's in a more accurate position than the lighter or thinner blue line that you see. Okay, so what else can we say? What about the focus points? The focus points would be here, somewhere there, and on this side. So that would be focus, let's say focus number 2, focus point number 2, and this would be C comma 0, and this would be focus point 1 at minus C comma 0. Okay, like that. So that is associated with that equation. And this one, let's draw the central box for this. I think this was drawn better than the other one. So suppose we have our central box here. This is a more symmetric figure than that one. It looks to be that way. And then like that, yes, this is much better than the other one. And of course that one. Oops, like that. And then connect these 2 points. Okay, as you can see, with the central box is a box where the asymptotes go through the corner points, and so it defines the location of the asymptotes. We have equations of these, and I will put that on the drawing in a minute. But each of these asymptotes has its own equation, particular to this equation of the hyperbola for this case and for that case. So because this one, the vertices are associated with the y squared term, or they are the denominator of the y squared term, and A being the quantity associated with the vertices, then therefore this is a vertical asymptote, which means it opens up and down like that. And notice that the vertex of the hyperbola touches that point of the central box, and one goes here and here. Okay, so let's label these points. Once again, those are the vertices are associated with A, quantity A, so that would be 0 comma A, and this would be 0 comma minus A, and these 2 points are the B, so we'd have minus B comma 0, that point, and that point is B, positive B comma 0. Blue dashed lines are the asymptotes. The focus points, or I can make these a little bigger for that, and then here we would have that as a focus point and this as a focus point, and that would be, let's call that focus point 1 or F1, or the focal point 1, and that being 0 comma C, and this is focal point 2 with coordinates 0 comma minus C. Okay, So what about the asymptotes? The asymptotes for the horizontal hyperbola have their own equation. So this one, I guess it's better if I use the blue pen here, and let me use my thicker blue pen. So the equation of this asymptote, that one, is y equals minus b over ax. And this x is in the numerator. Well, let me draw this better at least. So that one, I guess, so this is minus b over a is the coefficient of x. Also minus b over a times x. So that's that. I rewrote it just to make that clear because it looks as if x is in the denominator. No. This is x is being multiplied by this whole thing. By that whole thing. By that ratio, minus b over a times x. And I made it more clear here. Let me box that like that. Minus b over a times x. So this one, it would be y equals b over a times x. Okay? So this is for the horizontal hyperbola. The asymptotes, the equation of the asymptotes can be determined using this. So it's basically plus or minus the same thing. Plus or minus b over a times x. That's the equation of that asymptote. What about here? Well, the equation of that asymptote, this is a vertical hyperbola, right? It would be equal to y equals minus a over b times x, and that one, this asymptote would be equal to y equals positive a over b times x, like that. Okay, so that's the equation of this asymptote. This is the equation of that asymptote. Notice there are the change in the formula for these asymptotes. First of all, you know this has to be the slope of x. This is just a linear equation, right? With the slope being negative. You already know this has to be negative, right? Because this is a downward sloping line. And this one has to be the positive one, a over b times x, because this is the upward sloping line. Okay, and the same thing here on this side, minus b over a, because it's sloping downhill, and this is sloping uphill that way. Okay, so for horizontal one, these are the things that it would be best memorized for each case, and memorize them as one, just plus or minus b over a for the horizontal hyperbola. For the vertical hyperbola, plus or minus a over b times x. Okay. So what else should we know about these hyperbolas? So let me, underneath each one, you have the equations on top. So let's list other properties for each one. And I want to draw a vertical line here so that they don't mix. So something like this. So properties of the horizontal hyperbola and the properties of the vertical hyperbola. So we have properties and properties on this side. So here we have the vertices are greater than, so A is greater than 0, B is greater than 0, and then vertex is at, because this is a horizontal hyperbola, so it has plus or minus A comma 0, and that's what we have, A comma 0 minus A comma 0, and here also A and B greater than 0, and these are distances, that's all. So minus B would be on the negative side, but B itself represents a distance. That's why we say that they are positive, because they represent distance. And then the vertex here, because this is a vertical hyperbola, right? So the vertices are at 0 comma plus or minus A, and the so the equation of the asymptotes for the horizontal hyperbola is plus or minus B over AX. So this is more clear. This formula is more clear than what I have here, right? Because it looks like as if X is in the denominator, but it's not. Okay, so that's that. And by the same token, the equation of the asymptotes for the vertical hyperbola is plus or minus A over B times X. And the focus point, or the foci, are at, for the horizontal hyperbola, are at plus or minus C comma 0. And here the foci would be, because this is a vertical hyperbola, so the focus points would be at 0 comma C and 0 comma negative C. So let's write that down, 0 comma plus or minus C. And of course, another formula that we haven't talked about yet, and that is that the formula C squared, that's the location of the focus point squared, is equal to A squared plus B squared. And also C squared equals A squared plus B squared. Okay, like that. So these are some of the additional properties of each type of hyperbola, the horizontal hyperbola and the vertical one. Okay, so I can't fit everything on this screen. Okay, so before we start going over some examples, let's see how we should go about sketching a hyperbola. Okay, so these are steps to sketch a hyperbola. Okay, so first we want to sketch the central box. That way our figures will be symmetric, as opposed to when I drew it here, I wasn't using any numbers. I just noticed there are no numbers here, so I just generally drew where the lines would be. But when we calculate these numbers and sketch the central box, that will guarantee that our figure looks just about right. So we start with that, sketch the central box, sketch the asymptotes, and the asymptotes go through the corners of that central box, right? They should go. So if this is the central box, the asymptotes are going through the corners of that central box. Okay, sketch the asymptotes. And remember for the vertical, so for the horizontal, this is plus or minus x, right? This is plus or minus x for horizontal hyperbola, and y equals plus or minus a over bx for the vertical one. Okay, so sketch the central box. So where is, I should say something about that. So the central box would be at these locations, depending on, well, depending on where the vertices are. So at vertices, so these locations, so maybe 0 comma plus or minus a, and plus or minus b comma 0, or they'll be either there or at plus or minus a comma 0 and 0 comma plus or minus b. Okay, so depending on what kind of hyperbola we have, right? So this one, with this kind of information, our hyperbola is vertical. Vertical hyperbola. With this one, our hyperbola is horizontal. Hyperbola. Okay. And then finally plot the vertices and sketch the hyperbola. So sketch the hyperbola. Did I say the focal point? No, so I should say that. Plot the focal points F1 and F2, right? Plot that. And we know what formula has to do with this. We just talked about it on the previous page, right? It was c squared equals a squared plus b squared. We use that to find the focal points. Sometimes it's given to us, so we don't even need to use this formula. Okay, but that's how. So for sketching the central box, that's what we will be looking for. For sketching the asymptotes, this is what we will be using for plotting the focal points. This is the formula. And finally, the number 4, we would sketch the hyperbola. Okay, so that's the path for us to drawing a hyperbola. Okay, so let's begin to go through some examples. I don't think what I have left on this page is enough for me to put my example there, so I'm going to go to a new page. Here, in this example, let's see what we want to do. So we are given a graph here. So let's start easy. That's good. So given the following graphical information, label and identify, or identify and label the vertices, remember hyperbola has only 2 vertices, not 4 like the ellipse. So vertices and foci, or the focus points, and asymptotes, and write the equation for it. That's good. So this is an easiest problem we can answer on this topic. Okay, and here's the graph. So the graph is given to us, and I want to draw it here. Like that. And so this time I want to draw the central box. That way my figure will be symmetric. So like that. And then like that. And also like this. Oops, I went too far there, but I'll try to mitigate that issue with my thicker pen, like that. So these sides should be equal to each other, and the asymptotes would be, so this is the central box, and the other piece of information we're given is that this is where the asymptotes are, going right through the corner points of this box, like that. Again, all of this information is being given to us. And then we're going to label this figure and then write the equation of the hyperbola that is associated with this. And we are told that this point, we are told that that point is 0, 4. We are therefore this point, it would have to be 0, -4, right? We are told that this point is located at 3, 0, and this point is located at -3, 0. Okay, and what else we are given? So, yeah, so this is, so we are also given information here, right here. Let me use one of my thicker markers here. We are given a point here, and we are told that the coordinates of that are 0, 5, and here the coordinates would be 0, -5 for that big dot. Okay, so now we need to identify the vertices, the foci, and the asymptotes. Well, the asymptotes are, let's start with the vertices. The vertices are always along the same distance, along the same axis as the foci. So that would be right here. Those are the vertices. And so I'd say vertices at 0, ±4. Okay, that's where they are, 0, 4, 0, -4. So that we did that. What about the foci? The foci, or the focal points, are at 0, 5, 0, -5. So this is plus or minus 5. Let me add, this is the added touch. You don't need to do this, but this is 0, plus or minus a. This is 0, plus or minus c, right? And then what about, they didn't tell us, they didn't ask us for the b terms, but we're going to need to identify them because they're asking us to write the equation at the end. So the b, and so let me just say that minus 3. So I'll say plus or minus 3, 0. That's these 2 points are equivalent to plus or minus b, 0. So now we have this kind of labeling of the variables a, b, c. Okay, like that. And asymptotes, this is going to be a vertical hyperbola, right? So so let's write this down for asymptotes. Because this is let me actually draw it so it's more clear. So this is the hyperbola going like that. The second piece is going to go like this, like that. So because this is a vertical hyperbola, the equations of the asymptotes let me move this up. The equations of the asymptotes are these two. Y equals a plus or minus a over b times x. So from here, one equation will be y, the one that is going downhill. The equation of the line that is going, the asymptote that is going downhill from left to right would have to be the one with the negative slope. And a here is 4 divided by b, which is 3. So minus 4 over 3x. That's the equation of that asymptote. Asymptote y equals minus 4/3 x. And the equation of the other asymptote, the one that is going uphill from left to right, we should be the one with the positive slope, right? So y equals 4/3 x. So that would be that one. I guess I can draw it on the drawing here. That asymptote is y equals 4/3 x. Okay, so this one is sloping downhill from left to right. So it has this equation, y equals minus 4/3 x, and y equals 4/3 x because this one is the one that is sloping uphill going from left to right. And this is all given to us. We discussed this here for the vertical hyperbola centered at the origin. Then it is plus or minus a over b times x. So that would be plus or minus 4/3 times x. Okay, so we've done everything they've asked for except write the equation for this. So the equation of this hyperbola would be y squared over a squared minus x squared over b squared equals 1. Right? Because this is a vertical hyperbola, so the a squared term, which is associated with the location of the vertices, is the denominator. That quantity is associated with the denominator of y squared term, and the rest is just minus x squared over b squared equals 1. So that, then let's plug in numbers, right? So for this specific case, so we have, from here, we have y squared over a was plus or minus a was plus or minus 4, so a is 4, and a squared is 16 minus x squared divided by b squared. B was 3, right? B was 3. So b squared is 9 equals 1. Like that. Okay. Let's do another example. So we want to, in this example, for the hyperbola x squared over 2 minus y squared, minus just y squared, equals 1. We want to find the vertices, the foci or focal points, and asymptotes, and sketch its graph. Okay? Okay, so the vertices are associated with the variable a in the hyperbola, right? So we know that in this case, the a squared is always the denominator of the first fraction. So we have a squared equals 2. Okay, so here's the solution. So we know from the equation a squared equals 2. That's what we know. Therefore, a is equal to plus or minus square root of 2. And plus or minus by the square root property, right? Also, the denominator of the y squared term is 1. That means b squared equals 1. So b squared equals 1. And that means b is equal to plus or minus square root of 1, which is just 1. Okay, so we know the location of the vertices, which is just the a equals plus or minus square root of 2. We know where, because we're going to have to draw the central box, right? To draw the central box, we're going to need the value for b as well. We have that. And they ask us to find the value of the focal points or foci. So that would be, we have an equation for that. C squared is equal to a squared plus b squared. In this case, it would be square root of 2 squared plus 1 squared. So we have 2, so the square root of 2 squared is 2 plus 1 squared is 1 equals 3. So c squared equals 3. Let's write that down. C squared equals 3. Therefore, c is equal to plus or minus square root of 3. Can we draw the hyperbola at this time? Yes, we can. Also, that a squared is associated, is the denominator of x squared. So this is it a vertical hyperbola or a horizontal one? Do you remember? It is a horizontal hyperbola. So from this, I should make a note of that. From this equation, we know we have a horizontal hyperbola. Okay, so these vertices plus or minus square root of 2 are along the horizontal axis. Let me actually say that. So we have square root of 2 comma 0, and these two are the vertices, minus square root of 2 comma 0. So this is the vertices, and so this is the opposite of that. So because whatever axis that A is on, B would be on the opposite axis. So A is along the horizontal x-axis. That means B must be on the y-axis. That means we have 0 comma 1 and 0 comma negative 1. And of course, the focal points, these will be on the same axis as the vertices. So this will be, which in this case it would be horizontal. So it would be minus square root of 3 comma 0 and positive square root of 3, 0. So I should have maybe switched that here too, but they're both there. Okay, so we need also to find the equation of the asymptotes, right? For the asymptotes, because we have a horizontal hyperbola, then the asymptotes, the formulas are equal to y equals plus or minus b over a x for horizontal hyperbola. That's the equation of the asymptotes. Okay, so we can easily find we know A and we know B, so we can easily find the equations of the asymptotes. They will be y equals plus or minus b, which is 1, over a, which is square root of 2, and so 1 over square root of 2 x. But you know, in math by now, we want to rationalize the denominator as always. So therefore, we have y equals plus or minus square root of 2 over 2x. So that's the equations for both asymptotes. Okay, the negative one is the asymptote that is sloping downhill, and the positive one, the asymptote that is sloping uphill, from going from left to right. Okay, so can we draw the, can we sketch the graph? Absolutely, we have all the information we need. So let's do that. So these numbers are pretty small numbers. So square root of minus square root of 3 is square root of 3. Is that 1.6 something? We can quickly get a feel for those numbers. And then square root of 2 minus square root of 2 minus square root of 2, that's just 1.414 and so on, right? So just ballpark idea what these numbers are. And also square root of 3, it is 1.73 something. So less than 2 basically. Okay, so I'm going to make my increments 1 and 2. So those are easy numbers to work with. So let's say that's 1, and this is 2, and let's say minus 1 and minus 2, and also 1, 2, and then minus 1, minus 2. Okay, so A is at square root of 2 and negative square root of 2 comma 0 along the horizontal axis. That's 1.414 along the horizontal axis. So that would be somewhere, if this is minus 1 and that's minus 2, minus 1.5 would be in the middle, and minus 1.414 rounded to for square root of negative square root of 2. So that would be slightly this way on this line, on this horizontal line. So that would be minus a comma 0, or minus square root of 2 comma 0, and square root of 2 comma 0 would be slightly toward this, so it would be here. Okay, so that location is minus square root of 2 comma 0. I know I'm writing this small, but these drawings tend to get really crowded, so I'm trying to avoid that as much as I can. And then this point, that's the other vertex. It would be square root of 2 comma 0. So minus a plus a. And then where are the B locations? So the B locations are at 1, plus or minus 1, right? We figured that out here, because the denominator of y squared was 1. So that's b squared equals 1 in this case. Okay, so that's easy. That would be 0 comma 1, and then of course 0 comma negative 1. Okay, so we can easily draw the central box. Let me do that with blue ink. And you can see when numbers are involved, the graph is going to look a lot better than what I drew just random with random lines. So without any numbers. So this one would be roughly here. And let me connect those two through that. And this is those two connected through that. Okay. So this being a horizontal hyperbola, the focal points would be at these locations, which are square root of plus or minus square root of 3 comma 0, which we just saw in the calculator. It's 1.73 something, right? So 1.73 something, that would be less than negative 2 and less than positive 2. So it would be on this side here. I'm going to just plot it here and make another point here. And that, let me write down in thick, using the thick marker, that is equal to minus square root of 3 comma 0, and this is equal to square. So those are the coordinates of the focal points. Okay, now we can draw the asymptotes, right? The asymptotes will be will be in much more accurate place than what I drew before, since numbers are involved here. So 1 will go this way, like that, and 1 will go this way. Notice that the asymptotes are going through the corner points of the central box and through the center of the hyperbola, right, which is at the origin, like that. Like this. And what is the equation of each of those? Well, we know that that's the equation of the asymptotes we had. We know that the negative one should be the slope of, or the equation of the line that is sloping downhill. So this one is y equals minus square root of 2 over 2x. And the equation of the one that has an uphill slope would be the positive one, positive square root of 2 over 2 times x. So those are the asymptotes. And of course, finally, let's draw the hyperbola itself. So these are the two vertices, right, on the central box. So I will come this way, like that. Like this, and another curve going through that vertex like that. Okay, so this is our hyperbola, which has the equation is off the screen. Let me write it here. So we were given x squared over 2 minus y squared equals 1. So there's the equation of the hyperbola. And those are the equations of the asymptotes. Okay, so let's do another example. All right, so this example, what's worth noting, guys, is that all the examples we've done so far, the coefficients of x squared and y squared terms were 1. But in this case, we have a coefficient for x squared and y squared that is not equal to 1. In other words, 9 for x squared and minus and 16 for y squared. So how do we deal with situations like this? Now, notice that the number on the right-hand side is still 1. So in order to end up with the standard equation for a hyperbola, we need the other side to be equal to 1. So the other side is already that. We don't want to change that. But on the left-hand side, we need to change the way this equation is organized, so the value of a squared and b squared, which are the distances from the origin to the vertex, a squared or a, and b values are clear for us. Right now it's not. So let's reorganize this. How else can we rewrite this equation So the values of a and b are more clearly shown. All we have to do is just rearrange the left side a little bit. So instead of writing 9x squared, we're going to write it this way. We have x squared divided by 1 over 9, right? If this is a complex fraction, but if you simplify it, you'll get that. Minus y squared divided by 1 over 16. And that is equal to 1. Okay, so just we rearrange the left side so that now the coefficients of x squared and y squared is just 1. But if you look at the denominator, now we can draw from these denominators what a and b are, because we know what a squared and b squared are. Okay, so the larger value is always a, or in this case, the denominator is a squared. So this would be our a squared. So if a squared is equal to 1 over 9, then what do we know about a? A would have to be plus or minus 1 over 3, right? Square root of both sides. And by the square root property, which we learned about in basic algebra, college algebra, we end up with plus or minus 1/3. So knowing a, then we know where the vertices are located, right? Which is one of the items we need to find. So from this, we can know that vertices are at, and this is the larger number, is under x squared. So we have a horizontal hyperbola. And so this would be, so that means my point of the, by mentioning that is that the a would be along the x-axis. So we'll just say then minus 1/3 comma 0 and 1 positive 1/3 comma 0. And that's going to be along the horizontal or x-axis. By the same token, we know what b squared is. B squared is 1 over 16. So if b squared is equal to 1 over 16, then we have b, take the square root of both sides, we end up with plus or minus 1 over 4. So therefore then, and so this, and then of course this would be, this would be that box, the box that we mentioned, the central box that we initially mentioned in the previous pages that we have to draw before we can draw the asymptotes and the hyperbola. So then, so that would be on 1 over 4. So that would be 0, comma 1 over 4, and 0, comma negative 1 over 4. All right, so they're also asking us to find both foci. Okay, so the foci are going to be on the same axis as the axis that has the vertices on it. So in this case, the foci will be along the horizontal x-axis. Now, we have a formula with which we can calculate the value of it. We know that c squared is equal to a squared plus b squared. So from this, then we know that c would be equal to square root of a squared plus b squared. And of course, this is, once again, just like these, this will be plus or minus of that value. So we have plus or minus a squared is, again, we know it's 1 over 9, plus b squared, which is 1 over 16. And then if we take the common denominator of what's inside, we will get, I believe, 9, 6. So this will be 144. So we'll have 144. And then we have 16 plus 9. So we'll end up with plus or minus square root of 25 over 144, which is, so from that we know that C is equal to plus or minus 5 over 12. In other words, the foci are at along the, they're going to be along the horizontal axis as we established. So we're going to have minus 5 over 12 comma 0 and positive 5 over 12 comma 0. Okay, so we found the foci, we found the vertices, and on the central box we found where the B is located. The other thing we should find out, and they're asking us to, are the asymptotes, the equation of the asymptotes. We need to do that before we sketch the graph. So because this is a horizontal hyperbola, actually let me write this down. Because this is a horizontal hyperbola, then the asymptotes, the equation of the asymptote is based on that, right? So the equations of the two asymptotes, and these are slant asymptotes, are going to be y equals plus or minus b over ax. Okay, and we know what b is. It's plus or minus 1 over 4. We know what a is, plus or minus 1 over 3, and we can easily calculate the equation of the asymptotes. So let's do that. So we have y equals plus or minus b, which is 1 over 4, divided a, which is 1 over 3. Therefore, the equation of the asymptotes are as follows. So we have just, this is a complex fraction. When you simplify it, oops, I should add the x here. So plus or minus, simplify this complex fraction, you get 3/4 x. Okay, and this is the equation of the both asymptotes. So now the only thing left for us to do is just draw this hyperbola. So let me, and the equation, of course, tells us, this equation tells us the origin of the center of this hyperbola is at the origin, right? It is centered at the origin, so that simplifies things. The vertices are off of the origin, but that's that's where the box, the central box should be. So let me draw that. I hope I can fit it here in this little space that I have left at the bottom of this page. I think I can, so let's see. So here we have our x-axis and the y-axis. Note that all these numbers that we have, 5 plus or minus 5 over 12, and which is where the foci are located, and 1/4, 1/3. These are very small numbers. So let me pick my increment very large. So I'm going to pick 1 unit because of this denominator being 12. I'm going to divide one increment, or 1, 0 to 1, to 12 little increments. So let me do that. And So this will be, especially along the x-axis, I need to do that in order for my graph to be as accurate as possible. So 1, 2, 3, 4, 5, 6, 7. So that's 7, 8, 9, 10, 11, 12. And so this is 12. Like that. And then let me do the same thing on this side. 1, 2, 3, 4, 5, 6. So that's 6, 7, 8, 9, 10, 11, 12. So I'm sure I'm off, but I tried to make these increments as accurate as possible. So these are actually what I meant to do, and I think so this is like that. So what I meant is that, and I'm going to use my thick marker or thick Sharpie here, that to divide increment 1, so this is 1, and this is 0, and this is -1, to divide one increment of 1 to 12 subdivisions or increments, so that we can plot those points that we need to. So that's that. So this is from here to here is just 1 unit, but it's divided into 12 smaller increments. That's what I meant to draw. So from here to here, it's not 12, it's 1 unit, but it's divided into 12 increments. All right, so then let me do the same thing. I'll just divide this along maybe, along the y-axis, maybe 5 increments. That's all we need. 1, 2, 3, 4, 5. So that's, so this would be 5 over 12 actually to get to that. But let me do the same thing on this side. 1, 2, 3, 4, 5. Okay, so now I'm going to draw the central box first. The central box, that'll help me draw the asymptotes much easier. So this being the origin, the A is 1/3 of that of the 1 increment. So this will be 12 divided by 3 or 4. So that's where the vertices are. So 1, 2, 3, 4. And these are, of course, negative. Like that. But of course, that's 1 increment from here to here divided into 12 sub-increments. And so that's 1/3. The 4 represents 1/3 of the 12 increments. And on this side, we'll do the same thing. And here, I can see my box, my central box is going to be off. Then B, it's going to be 1/3 of the increments, of the 12 increments. 1/4 of 12, it's going to be 3. And that's going to be along the y-axis. So 1, 2, 3, 1, 2, 3. Okay, that's 1/4 of 12, which is 3. Okay, so now I'm going to draw my central box. We could draw this a lot, we can draw this more casually, but it won't be accurate as I want it to be, that's all. So I'm trying to make this as accurate, but this can be drawn much more casually. And I think your homework assignments on WebAssign do that. They don't draw the central box, for example, they just draw the curve where they ought to go, which is fine. So we know now that the hyperbola is going to go here and then here. So where are the asymptotes then? We know the equations for them. This is the equation for the asymptotes. Minus 3/4 x would go this way, downhill, right? So if I draw this with my red ink here, going right through the origin, so not bad. I'm not that off. My asymptotes are not that off. So this is the equation for this is y equals minus 3/4 x, right? It's minus, so it's going downhill. And the one that is going uphill, it's going to be the positive one. Not bad. So, all right, so this is going to be like that. And the equation of this, of course, will have a positive slope, right? 3/4 x. And I apologize for smearing the ink there. And so now we can draw the hyperbola, and I'm going to use my thick Sharpie for that. It's going to go from here to here, and from here to here, and also from here going through there and coming this way. And of course, I need to locate the foci, which are determined by the value for C. C was 5/12, plus or minus 5/12. So out of those increments, so we know that that's four increments determine where the vertices are. This is the foci are at 5/12. So that's where it's going to be the foci, right there. And on this side, there it is. And of course, I will just try to identify it better. So this would be 5/12, comma 0. And that will be negative 5/12, comma 0. And these are the foci. Okay. And the vertices are at minus 4/12, or 1/3 on this side and this side. So again, I just drew these increments because the numbers are really small, and I hope this is making sense. If you look at these numbers as the sub-increments, the main increment is from 0 to minus 1, and from 0 to 1. Okay, then these numbers will make sense. And of course, these are the b values. So that will be 1 over a positive 0, comma 1/4, and that one will be 0, comma minus 1/4. And these are the vertices. The drawing is really crowded, so I don't want to put more information. But that point, the vertex will be is the A equals negative 1/4 or negative 1/3, comma 0. This one will be positive 1/3, comma 0. Okay. So that will be that. And the main reason I picked this example again, it's because the coefficients of x squared and y squared are not equal to 1. So this is the technique we use because the other side is equal to 1. Then we don't want to change anything about the 1, so we're going to rewrite the left-hand side as that. And that'll tell us what a squared and b squared are in this case. And a squared is always the larger number. Okay, so the next example we have, in this case, we want to find the equation for the hyperbola whose graph is shown. So I wanted to draw this graph beforehand. So the graph is already given to us, and we're supposed to find an equation for this hyperbola. The things that are worth noting immediately is the location of the vertex. So if this is, notice that the center is at the origin once again. The center of this hyperbola is at the origin. The vertex, one of them is given to us. It's 2 square root of 3 comma 0. So the other one must be negative 2 square root of 3 comma 0. The other thing that you should notice is that this is a horizontal hyperbola because these curves open towards the horizontal axis. And therefore, because this is a horizontal hyperbola, then we can right away write a standard equation for it. So because this is a horizontal hyperbola, I should have said the standard equation. So not the equation yet, we're going to find that. But the standard equation, or the general standard equation, is going to be like this. It's going to be, so the larger number, or a squared, is going to be under x squared. So a squared minus y squared over b squared equals 1. So that's our general equation. But we need to know what they're asking us, not this, but what we can easily write this down, but what is a squared and b squared now? That's our next task, okay? So we already know what a squared is going to be, so let's, because of the information given to us here. So if a from this drawing is equal to 2 square root of 3, then a squared, of course, is 12, right? A squared is 12. So let's plug that into this equation. So we have x squared divided by 12 minus y squared divided by b squared equals 1. So how are we going to find b squared? Because if we were given the focal points on this side and on that side, we could easily figure out b squared, right, from that formula. Because we know c squared is equal to a squared plus b squared, so from that we could find b squared, which would be c squared minus a squared. But we don't have the focal points which would be equal to c. So what else do we have? Notice that we have the coordinates of a point on the hyperbola. This is a very important piece of information, right? Because this is x, this is y. So in this equation, because this point is on the hyperbola, we can plug that information into this equation. And let's do that. Let's and see what happens. So we have, so given, I'm going to say, given that 4 comma 4 is on the hyperbola, then we can easily say, okay, so 4 squared over 12 minus 4 squared over b squared must be equal to 1, right? The point 4 comma 4 is on the hyperbola, so we can easily substitute for x and y with those coordinates. And when we do, look at this equation. The only missing piece is b squared, so we can easily solve for it, right? Let's do that. So we have, on the left, we have 16 over 12 minus 16 over b squared equals 1. And then, so let's swap these. So 16 over 12 minus 1 equals positive 16 over b squared. We're trying to solve for b squared, right? And then, so what do we have? Let me, so I can continue this way. So we have, let's take the common denominator on the left. So 12, 16 minus 12 equals 16 over b squared. And then this, simplifying that, let me come up here and continue. So we have 16 minus 12, that's just 4 over 12 equals 16 over b squared. Now we can, so this simplifies to 1 over third equals 16 over b squared. And then if we cross multiply, right, 1 times b squared equals 3 times 16, right? Just cross multiply because we have an equality symbol in the middle. We can easily do that. We have one fraction on this side, one fraction on that side. Cross multiply, what do we get? We get p squared equals 48. That's all we wanted. So now in our equation, so we had, so thus, so knowing that, we can easily write thus the equation of the hyperbola is as follows. So we have x squared over 12 minus y squared over 48, of course, equals 1. Okay, like that. So this point that we were given on the hyperbola was key given the fact that we didn't have any information about the focal points, the C. Okay, so that's that. Another example, let's do another example here. We want to find for the hyperbola that satisfies these conditions. So we have a set of conditions given to us. So given, and the foci are at 0, at 0, comma, plus or minus 10. Right from the start, this is a pretty important information, right? Because the foci are always on the same axis for a hyperbola as the vertices are. So if the foci are on the vertical axis, then the vertices are on the vertical axis. So this is a vertical hyperbola, which tells us that the equation, and let me start the solution right away, because this is a vertical hyperbola, the equation has to be of this form. So because, and we still have more conditions, but I want to just make a point here. The first condition is pretty important. It gives us a lot of information because this is a vertical hyperbola. Thus, the standard equation is as follows. We have y squared over a squared minus x squared over b squared equals 1. Okay? So that's that's what we get from this. So we already know it's going to look like that, our final equation. And then all we have to do is find a squared and b squared, right? And the other piece of information we are given is that and vertices are at 0 comma plus or minus 8. So we know what C is, we know what A is given these pieces of information, so we can easily find B squared. Okay, so using, and my blue ink is running out, I think. So using this equation, C squared is equal to A squared plus B squared, then we can say that, so C is already, we know it's equal to 10. So this would be, C squared would be 10 squared. Move this up a little bit. 10 squared equals A squared. A is equal to 8, so 8 squared plus, of course, B squared. So this is just now a matter of solving for B squared using algebra. So we have 100 equals 64 plus B squared. Therefore, B squared is equal to 100 minus 64, or 36. And that's all we need to plug in here. We already know this is 64 because it's 8 squared. So we know B squared is now 36. So therefore, we have our equation. So therefore, we have y squared over 64 minus x squared over 36 equals 1. Like that. Okay, so that's another example for us. Let's do one more example that it's a little bit different than these. Suppose we want to find so these conditions, that the foci are at 0 comma plus or minus 1. Notice that the foci are once again on the y-axis. So this is again a vertical hyperbola. These conditions, this one, and also that the length, we are told that the length of the transverse axis is equal to 1. Okay, so given that information, we want to find the equation of the hyperbola. So solution. Okay, so we have, let's see. First, let's remind ourselves what transverse axis is. Is distance between the vertices between the vertices in a hyperbola, so between the values that we call a. So therefore it would be, so 2a. So thus, let's write that down here. Transverse axis is equal to 2a. Okay, like that. So, and one thing I mentioned earlier, that because of the location of the foci, we know that this is a vertical hyperbola. So let's also write that down. One, then we have a vertical hyperbola with the standard equation, which is equal to y squared over a squared minus x squared over b squared equals 1. Okay, so that's the standard equation. And when, of course, we need to find a squared and b squared. So from the transverse axis, because we know it's equal to 1, so we know 2a equals 1. From that equation, we can find a squared. Okay, so let me write that down. So because equals 1, therefore 2a equals 1, therefore a is equal to 1/2. Okay, a equals to 1/2, therefore a squared is equal to 1/4. Okay, so also we are given the foci, so we know what C is, so we can easily find b squared. Okay, so let's do that. So because we know this, and so we know that c squared is equal to a squared plus b squared, then let's plug in. From this information, we know that c equals 1. So we're going to plug it in here. So 1 squared equals a squared. A squared is 1/4. A is 1/2. A squared is 1/4. Plus b squared. Right? So from here, b squared is equal to 1 minus 1/4, or b squared is equal to 3/4. Okay, these are the important quantities that we're finding. So now we can easily write down the equation knowing that we have a vertical hyperbola. So y squared over a squared minus x squared over b squared. Let's put that together. So because, again, because our equation is this, we have y squared over a squared minus x squared over b squared equals 1. So then y squared divided by a squared, which is 1/4, minus x squared divided by b squared, which is 3/4, must be equal to 1. So let's simplify this a little bit. What do we get? We get, so this is a complex fraction. Simplifying it, we have 4y squared over 1 minus 4x squared over 3 equals 1. We don't have to write the 1, but I just wrote it to be clear what we're saying after simplifying that complex fraction. So that's the equation of the hyperbola we were looking for. Now, I just wanted to, the transverse axis, we talked about it here as being 2a. I just want to make sure that, let me draw a graph of this. I want to make sure that everybody's clear what we're talking about when we're saying transverse axis. So just a quick graph would make that clear. They're not asking us to draw the graph, by the way. I'm just doing it for clarity. Like that. And then we have, so 1 was the focal point, and then half of that was the vertex, or A, right there. So this is 0, 1. That is 0, 1 half, but I'll draw that later. And then we have that as 0, minus 1 half, 0, 1 half, and then of course the 0, minus 1. Okay, so I'll try to draw this as best as I can. The hyperbola is like this. It's going through, it's coming here, going through that, and then doing that, like this. And then on this side, it's going through that, like this. Like this. And then, so the transverse axis is 2 times A. So this is A from here, from the origin to 0, 1, that's C. So this is C. Let me just make that clear. This is C. This is C. This is A. And then, do I have a highlighter? I do. I'm not sure if I should use it because now it's going to smear. Hopefully it doesn't smear the ink, but the transverse axis is this distance. From A to A. From vertex to vertex. That is the yellow highlighted distance is the transverse axis, which is 2A. So the highlighted portion transverse axis is the highlighted portion. Okay. So this example wraps up our discussion of the hyperbolas that have their center at the origin. In the next sections, we will look at these conic sections when their origin or their center is shifted away from the origin of the axis. And I thank you for watching the video until this point, and I hope to see you again. For now, have a nice day.